Now, for those molecules that are actively reabsorbed, that is through energy expenditure in the form of ATP, there is going to be a point of saturation or a transport maximum. That means that if the concentration in the filtrate is so high that it exceeds the capacity of the transporter molecules to move them across the epithelium of the tubule, then these solutes are going to continue through the nephron. Now, there's still a chance that they can be reabsorbed in the distal convoluted tubule, but many of these excess molecules are going to be excreted. Now, a good example is vitamin C. Now, whenever you're feeling sick, you may take vitamin C in order to fight off the infection and to boost your immune system. And there are some people that will argue that if you take 2 or 3 grams of vitamin C, that's going to be better than taking just 500 milligrams or a single gram. But it turns out that anything above 1 gram really exceeds the capabilities of the kidney to reabsorb the vitamin C. And most of that excess vitamin C is then simply excreted. Okay, so now we are going to move to a section on what happens in the loop of Henle. Now, the loop of Henle is a critical structure in the kidneys of mammals, but also of birds, because the loop of Henle is a structure that allows us to concentrate the urine, actually to make the urine hyperosmotic, that is, making it have a osmolarity that is higher than that of the blood. The process that we are going to see is referred to as countercurrent multiplication. But in order for this countercurrent multiplication to work, we first need to talk about what is oftentimes referred to as the single effect. Now, to understand the single effect, we need to know that the descending loop of the loop of Henle is permeable to water and solutes. So it allows for the free movement of water and solutes. On the other hand, the ascending loop, that is the thick segment of the ascending loop, is not permeable to water. And it is also a site of active transport of salts out of the loop of Henle. So, we can see in this figure here 2 tubes that represent the descending limb and the ascending limb respectively. And I'm going to get my laser pointer out. So here we have the descending limb, here we have the ascending limb. The little dots represent the sodium, that would be the brown dot, and the chloride ions, that would be the green dots. Now, remember that the descending loop is permeable to water and sodium and chloride, so these molecules can move freely across the membrane. On the other hand, on the ascending loop of Henle, we pump out sodium chloride actively. Now, what this will produce can be seen in this panel over here. We start seeing an increase in sodium and chloride in the interstitial fluids and the descending loop of Henle, and the concentration of these solutes is lower in the ascending loop. So what we are doing is create high concentration over here and low concentration over here. Now, this process is key to the way that countercurrent multiplication works in the kidney. And I want to illustrate that with these figures here. Now, before we talk about the details, I want to set the stage for what I'm going to do here as I explain countercurrent multiplication. In the kidney, blood is filtered continuously, so there's always going to be a steady flow of filtrate through the nephron. But what I'm going to do here in the explanation is, well, I'm going to stop the flow, at least conceptually. Then I'm going to apply the single effect, and then I let the fluids flow again, stop them, let the single effect occur, and then allow the fluids to move again. So let me move on over here to the left-hand side of this figure. The solute, or the filtrate rather, as we have already mentioned, is at a osmolarity of about 300 milliosmolar per liter. So let's start with this value throughout the entire loop of Henle. Now we are going to turn on the single effect. That is, we allow the ascending limb to pump out sodium chloride into the interstitial fluid. Because the membrane of the descending limb is permeable to water and these solutes, we're gonna create a concentration of about 400 milliosmolar per liter in these two spaces, and we're going to decrease the concentration within the ascending loop. Now, this is represented by the squiggly line here, we're gonna allow the filtrate to move. So new filtrate comes in up through the proximal convoluted tubule. So that brings in new filtrate with a concentration of about 300 milliosmolar per liter. All the fluids that are at a 400 milliosmolar per liter now are being displaced, and they move down the descending limb and up the ascending limb. Note that at this point, at the tip of the loop of Henle, we already have a 400 milliosmolar solution. Alright, we're going to stop the flow. Here we're going to let the single effect work again, which is going to remove sodium and chloride from the ascending limb via active transport, which is going to reduce this upper section here in terms of its osmolarity. And we're going to again increase the osmolarity inside of the interstitial fluids and the descending limb. Now, because of the gradient that we had already set up here, we have 300 milliosmolar and 400 and 200. We now are actually enriching the tip of the loop of Henle to about 500 milliosmolar. We can see that the osmolarity is gonna decrease as we move up the loop of Henle. Now we let the filtrate flow again, as illustrated by the squiggly line. New filtrate comes in at 300 milliosmolar. It's going to push down the filtrate that is already having a higher concentration of sodium and chloride, and it's going to have a higher osmolarity. And it's going to push it through the loop of Henle. And now we can see that we have 500 milliosmolar stretching all the way through to the ascending limb. Now we stop and let the single effect take over again. And now again we are actively transporting sodium and chloride into the interstitial fluids and the descending limb. And see that at this point we have increased the concentration at the tip of the loop of Henle to already 600 milliosmolar. We let new filtrate come in. It's displacing the filtrate in the loop of Henle down the descending limb and up the ascending limb. Then we stop the flow, we start the single effect again. And we can see that now we are at 700 milliosmolar at the tip. We repeat this process many times and we get to above 1,000 milliosmolar. So we see that we have a mechanism to set up a concentration gradient and a osmolarity gradient inside of the kidney. Now at this point you may be a little bit puzzled because the ascending limb, as the filtrate exits the ascending limb, it has a very low concentration, a very low osmolarity, but wasn't all this process about actually increasing the concentration, making our urine hyperosmotic? Well, we're going to see how that happens in just a moment. But at this point, the important thing is to understand that we have a concentration gradient in the kidney. Now here we can roughly see how this concentration gradient plays out. So from the top to bottom of the loop of Henle, we have a differential of 600 milliosmolar, whereas comparing the ascending limb and the descending limb, we always maintain roughly a osmolarity differential of 200 milliosmolar. Now the filtrate is going to move into the distal convoluted tubule, where we have the regulation still of some ions, of some solutes that are important for the physiology of all animals: potassium, sodium, calcium, and we also can still regulate the pH by either retaining or excreting hydrogen ions or bicarbonate. Now the distal convoluted tubule is also the primary site for the kidneys part of regulating calcium. You remember which hormone was responsible for calcium regulation? Well, it does not only act on bones, it also acts on the kidneys to allow for the retention of this very important ion whenever needed. Okay, let me quickly move to the collecting duct. Remember, we still had the question, how are we going to concentrate the urine if in the ascending limb we are producing very dilute urine? So we're missing something, and that something happens actually in the collecting duct. It is here that the gradient that was set up by the countercurrent multiplication system is used to regulate the osmolarity of urine. It's right here. So it's not just a collecting duct in the sense that, well, here we have a tube that simply makes sure that the filtrate moves into the renal pelvis. No, this is still a physiologically very active site for regulating the osmolarity, the ion concentrations, and the water volume that are about to be excreted. This is also the site where we concentrate the urea, as we're going to see shortly. So here are two figures that show what happens in the collecting duct under two different conditions. The first one being antidiuresis and the second one being diuresis. Antidiuresis leads to very concentrated urine and little fluids being excreted. Diuresis, on the other hand, produces dilute urine and usually larger quantities of water that are being excreted in the urine. Okay, so let's see what happens in antidiuresis first. Now this graph shows with these yellow bars the sites of the nephron that are impermeable to water and salts. So water, sodium, and chloride cannot freely move across these membranes. Now we know that in the ascending limb we can transport sodium and chloride actively, but the sodium and chloride cannot diffuse back into the ascending limb. Now, the filtrate, which is at about 100 milliosmolar, is now going to move through the collecting duct. We see there's no longer a yellow line. That means that the collecting duct during antidiuresis is permeable to water. It's permeable to water. Now, as this very dilute filtrate comes in, it's going to encounter in the interstitial fluid a much higher osmolarity. That is that some of this filtrate, of the water in the filtrate, is going to diffuse into the interstitial fluid because we have a higher concentration, a higher osmolarity in the interstitial fluid. So step by step, the filtrate is going to move through this concentration gradient that we had set up during countercurrent multiplication. Every time as the filtrate moves, it's going to encounter on the outside in the interstitial fluid a higher concentration, and that means water is continuously going to leave the collecting duct and move back into the interstitial fluid, and from the interstitial fluid it's going to move back into blood circulation. The result is that because we let the filtrate come into an equilibrium with the interstitial fluids, by the time the filtrate exits the collecting duct, it will be at 1,000 milliosmolar, the same as what we find in the interstitial fluids. So throughout this entire process, what we are doing is removing water. Water is exiting the collecting duct, and thereby it increases the concentration of solutes in the filtrate. Okay, end result is we are going to excrete very concentrated urine in small amounts. That's what antidiuresis is, holding on to the water. During diuresis, on the other hand, we are going to get rid of a lot of water. Remember that a diuretic is a medication that helps us go to the bathroom. It gets us to urinate. Now, during diuresis, the walls of the collecting duct also become impermeable to water. And that means that the filtrate that moves through the concentration gradient here is not going to lose any water at all. Water is going to go straight out. It cannot diffuse out into the interstitial fluid. At the same time, in the walls of the collecting duct, we actively pump sodium and chloride out from the collecting duct into the interstitial fluid. The result is a large amount of urine that is very dilute, here with a osmolarity of only 65. Alright, during antidiuresis, the collecting duct is permeable to water, and therefore we can concentrate the urine. During diuresis, the collecting duct is impermeable to water, and that means the water is going to move down the collecting duct into the renal pelvis, and then it's going to be excreted. Make sense? Well, I hope it makes sense. If not, you can always ask me questions in class. Now here we have a figure that looks very similar to the previous one, especially with regards to sodium and chloride and water. But I want to use this particular figure to talk about urea, because urea can also be excreted, in low or high quantities. Now again, the collecting duct is going to be crucial for the process of concentrating the urea. Now our filtrate moves through the collecting duct, and here towards the medullary section of the collecting duct, urea exits the collecting duct into the interstitial fluid. Now from here, the urea is actually gonna re-enter the loop of Henle, the ascending limb, where it is going to be taken again through the remainder of the nephron until we get to the medullary portion of the collecting duct, where again the urea is actually diffusing out passively. Now, how does concentration work here? Let's start with the loop of Henle with 0 amount of urea. And now we're going to move urea through from the Bowman's capsule into the proximal convoluted tubule and now into the loop of Henle. This urea is going to move. It's going to get here and then finally to the collecting duct. The concentration of urea in the interstitial fluids is 0. Therefore, urea is going to diffuse passively out into the interstitial fluid. Now from the interstitial fluid, it can be taken up again by the ascending limb, which is going to move it through here again. And because we have a low concentration of urea in the interstitial fluid and a higher concentration in the collecting duct, this higher concentration of the collecting duct stems from the fact that new urea is coming down and old urea is taken up again by the ascending limb. So now this higher concentration here is going to meet a concentration that is lower in the interstitial fluid, and we have diffusion out of the collecting duct. Now new urea is going to come in, old urea is going to be added to this, and now the concentration here is already higher because we have had 2 events of diffusion of urea out into the interstitial fluid. The urea at the higher concentration is going to move through, and now because it's at a higher concentration than it used to be in the interstitial fluid, we have diffusion out. It's going to join the new urea that comes in. We move through this nephron again until we reach the medullary portion of the collecting duct, and we repeat the cycle. So every time we're moving urea through this portion of the nephron, we have a higher concentration inside of the collecting duct than the interstitial fluids and the loop of Henle, and therefore we're going to have diffusion of urea out and the cycling of the urea throughout the system. Eventually, the concentration will be so high in the interstitial fluids and in the ascending limb that an excess of urea is simply going to exit the collecting duct. Alright, I hope this makes sense. If not, again, please ask me in lecture. Alright, so here we have simply a few additional notes about what we have just seen. So the gradient created is used by the collecting duct to determine the final urine volume. So the collecting duct is key. Animals that must tightly regulate body water stores, such as desert animals, tend to have very long loops of Henle, which allows them to establish very large osmotic gradients inside of the kidney, which means that the urine can exit at a higher concentration, at a higher osmolarity. Of course, those animals that live in the water, in fresh water, that have to deal with the constant uptake of water, well, those animals don't really need to concentrate the urine. They need to make sure they get rid of the excess water. And that means that these animals don't have a loop of Henle. So here we have, for example, fish and amphibians. Now, if you paid attention to what I just said, there is a constant during antidiuresis. There's a movement of water out of the collecting duct into the interstitial fluids. So potentially what we're doing by moving that water is to dilute the interstitial fluids, but we don't want to dilute them because we want to maintain a concentration gradient. So what happens with this excess water that potentially could dilute our concentration? Well, it is taken up by those blood vessels that we saw earlier, the capillaries that move down along with the loop of Henle and back up into the cortex. Now, those capillaries are referred to as the vasa recta. They run parallel to the loops of Henle, and they do so to always adjust their osmotic pressure or their osmolarity according to the levels in the kidney, thereby assuring that the vasa recta only take up the excess of water and not all of the water that we recover through this process. Okay, so the vasa recta are important to get rid of this excess amount of water that comes in during antidiuresis that potentially could dilute the concentration gradient inside of the kidney. Alright, and because it parallels the flow of the loop of Henle and adjusts constantly to the changes in osmotic pressure and concentrations in the interstitial fluids, we lose very few solutes into the vasa recta. Again, if this doesn't make sense, please ask me in class. Now, just a couple of notes on a few hormones that are important in regulating kidney function. And first of all, we have aldosterone. Aldosterone acts on the distal convoluted tubule to stimulate the active transport of sodium out of the tubule. Now, this is a sodium-potassium exchanger, so we are actually moving out potassium at the same time. Now, the aldosterone stimulates this active transport to recover or to retain sodium that is still in the filtrate and the distal convoluted tubule. Now, because we setting up a concentration gradient across the epithelium of the tubule, water is going to follow the sodium passively down its concentration gradient back into the blood eventually. Alright, so here we have our epithelium of the distal convoluted tubule. These are the epithelial cells. Here we have the lumen, that is the inside of the tube, our interstitial fluids, and our capillaries. Aldosterone stimulates the functioning of the sodium-potassium pump, removing sodium out of the cell, which lowers the concentration of sodium in the cell, which makes the sodium from the luminar fluids to enter the cell passively, and then it's going to be pumped out actively. So the sodium is going to follow down its concentration gradient. Now the pump also brings in potassium, which leads to an accumulation of potassium inside of the cell. It gains a higher concentration than the fluids in the lumen, and therefore potassium will diffuse out into the lumen. Then eventually here the sodium is taken up because of the high concentration of sodium in the interstitial fluids. It's going to be taken up by the blood that has a lower concentration. The other hormone that I want to talk about is the antidiuretic hormone, or ADH, because it is important in determining whether or not the collecting duct is permeable to water. Now, the antidiuretic hormone suggests that it is going to be important for antidiuresis. And if you remember the figures from a few slides ago, during antidiuresis, the epithelial cells of the collecting duct are permeable to water. That is, water can exit the collecting duct and come back into the interstitial fluids. Now, ADH, what it actually does is to stimulate the movement of aquaporins into the cell membrane. Now, you may remember aquaporins from Biology 1. They are important channels that allow for the facilitated diffusion of water through the membrane. The more aquaporins we have, the more water can diffuse through the membrane. And the more ADH we have, the more aquaporins we will have in the membrane, and that means that the diffusion rate of water is going to be even higher. Now, where are these aquaporins usually? Well, these aquaporins are actually stored in vesicles. Let me draw this over here. Now, let's say this is the cell membrane with the phospholipid bilayer. Here we have vesicles inside of the cell that are also going to have a bilayer. Now I'm drawing with a touchpad, so this looks really ugly, but anyway. And in these vesicles we have aquaporins. Now what ADH does is to stimulate these vehicles to move to the plasma membrane and insert themselves into the plasma membrane, such that now we have the aquaporins inside of the plasma membrane, and water can diffuse quite easily across these transmembrane proteins. So this is H2O. All right. This movement then again is stimulated by ADH, the antidiuretic hormone. Which brings us to the last section. Whoopee! Nitrogenous waste. And I'm going to just come back to my laser pointer. Here we are. And we are going to talk now about nitrogenous waste. How do we produce nitrogenous waste? The main source for nitrogenous waste is amino acids or proteins. Why? As I mentioned earlier, our bodies cannot store proteins. We can store lipids and carbohydrates, but we cannot store proteins. So if we ingest in our diet more protein than we need to replace different proteins in the body. Any excess protein or any excess amino acid will be converted into carbohydrates and lipids. Now, the first step to produce carbohydrates and lipids from amino acids is to deaminate the amino acids. That is to remove the amino group from the amino acids. And as soon as we do that, we form ammonia or ammonium ions. That happens right away after deamination. Now, ammonia is pretty nasty stuff. It's not good for our bodies. Okay, so we need to think about, well, if ammonia isn't good for us, what else can we do to get rid of this nitrogenous waste? And for vertebrates, that means, by and large, the making of urea and uric acid. Okay, let's look at most aquatic animals. And we can see, actually I kind of liked the pen, we can see that the nitrogenous wastes are eliminated as ammonia and ammonium ions. Now you're gonna say, well, Profe, you just said that ammonia is toxic. Well, it is. But fish, through their gills, have the ability to immediately get rid of the ammonium. That is, as soon as the blood with the ammonium moves through the gills, it diffuses out. That is, the ammonium diffuses out. So fish never really have to allow the ammonium to concentrate in their blood. It's continuously removed. Now, this is a good thing for fish because this removal is passive, so it does not require any energy. Now, the amount of water required for excretion is obviously high, but the fish, where does it live? In the water. There's water. There's water everywhere. So it's not a problem for the fish. And obviously, the toxicity of this type of waste is very high as well. So fish can get away with production of ammonia because they can get rid of it all the time, even though it is quite toxic. Okay, let's look at other animals, terrestrial animals. Now, terrestrial animals have a problem with potentially desiccating. So terrestrial animals have to hold on to water. Now, holding on to water means that we are oftentimes in the need to store nitrogenous waste. Now, if we were using ammonia as our nitrogenous waste, that would mean that we would create toxic conditions in our system. We don't want that. So what do? Well, we convert the ammonia to urea. Here's the molecule. Now, this molecule has the advantage that, well, it requires some energy, but the requirement is moderate. It requires only moderate amounts of water for excretion, which is good for a terrestrial organism, and the toxicity is low. So it's great. Urea is a solution to store nitrogenous waste because ammonia is too toxic. And then finally, many reptiles and other animals use uric acid. Uric acid. Here's the structure. You can see it's a complex molecule, and if you think that it requires a lot of energy to make a molecule like this, you're absolutely right. energy requirement is high. But there are some advantages, and one of the great advantages is that we need very little water to get rid of our nitrogenous waste, because the uric acid precipitates out of solution. It no longer contributes to osmotic pressure, which means that we don't need large amounts of water to get rid of it. The toxicity of this molecule is also very low. Now, there are a couple of points that I want to make. The first is, well, I didn't give you an idea as to how much ATP is actually required for making uric acid. It's about 8 to 9 ATP molecules. Compare that to urea, which requires 4 to 5 ATP molecules to make a molecule of urea. Compare that to ammonia, which doesn't require any ATP at all. So it gives you an idea of the magnitude of how costly making urea and uric acid is. The other point that I want to make is about toxicity. The toxicity of uric acid is actually very low. Now, for birds, it has even been suggested that the uric acid may be partially responsible for birds being long-lived, because uric acid is a powerful antioxidant. So it protects the body from the negative effects of reactive oxygen species, that is, of radicals. So there are actually quite a few advantages to uric acid. Now, in humans, if we produce uric acid, it usually precipitates out in our joints, which becomes very painful, and it's a condition that we call gout, or in Spanish, la gota. So for us, excessive production of uric acid is not such a good thing. Okay, so yes, some terrestrial snails and crustaceans secrete ammonia as gas. Wow. But I mentioned to you previously, it's not just aquatic organisms that can excrete ammonia. There are some terrestrial organisms that do that as well. As a matter of fact, in the bird group, that is in the birds, yeah. Hummingbirds. Hummingbirds feed on a lot of nectar. As a matter of fact, the nectar being liquid forces hummingbirds to get rid of the fluids very, very fast. And as they move the fluids very fast through their body, those fluids can actually take up ammonia and be excreted as ammonia. It doesn't need to be converted to uric acid. Up to 50% in one species of nitrogenous waste in the species of hummingbird is removed in the form of ammonia, not uric acid. Why, again, can the hummingbirds do that? They can do that because they have a very high water content in their diet. Okay, so we've seen in the case of sharks, sharks regulate osmotic pressure by increasing the amount of urea in their blood. That comes in very handy, but urea can also become toxic, which is why sharks then had to produce TMOA, trimethyl oxide, and amine to counteract the toxic effects of urea. So it's less toxic in general, requires less water to be removed. And then finally, as I already mentioned, uric acid in birds, insects, and most reptiles. It's less toxic, but very costly to make. Okay, so that concludes our lecture on the excretory system. I hope you are not too wasted right now. Take a break, drink some coffee, and get ready for tomorrow's class. All right, see you then.